Hello everybody, thank you Chairman for announcing my lecture about finite element simulation of composites without dimensional reduction or homogenization with only hexahedral finite elements. In this slide you can see some of my references, one paper and one project related to the present approach and application. And the keywords of the present talk are composite structure, finite element method, reliability of finite element method, new finite element approach as a black box to the user, and also multiscale simulation. Interesting issues related to design of the composite structures are selection of the composite type, selection of volume ratio and of matrix and reinforcement, selection of number of layers, its position and final thickness of the composite, also the price of manufacturing, testing and attestation, and also prediction of behavior and failure modes and location of the failures. The goal of the present work is to announce the new finite element approach that is simple to use, that has straightforward transition from computer-aided design to finite element method, that it is reliable, that have only one finite element type, that is hexahedral finite element. It contains simultaneously displacement and stresses, and so boundary conditions for both variables can be introduced directly. Some of the usual stressful issues in the composite structural design and calculation are, for example, who will quickly, cheaply, and accurately tailor my new composite to maintain the strength of the old metallic part. And also, I can only use plate finite element type. So will I have some problems with extraction of data? And let's address some of these issues later in the presentation. So, as I said already, present approach is based on hexahedral finite elements only. It is robust, stable and accurate, which means that it is reliable, it is spatially multiscale, it is time efficient, and thus it minimizes the risk-related modeling errors and accurately determines possible failure modes and locations. In this slide you can see primo mixed formulation, which I named FEMIX. It is reliable even if its finite elements are extremely stretched and skewed. We will see that it is reliable up to 7 orders of magnitude in each of the finite elements. For present finite element approach, I have written in-house software FEMIX. It contains only one finite element type, that is hexa. It can be embedded between commercial preprocessor and in-house or commercial post-processors. It can be used also for material parameters identification, and can be used for standard and non-standard finite element simulations, for composite, rubber, coatings, and it is thermomechanical. In this slide we can see the results of IMSUP test with which we have proven the reliability of the present formulation, and you can see that a very thin clamped plate. It's simulated with the number of finite elements per thickness, and that brick aspect ratio are very big, much bigger than allowable in usually used software packages. Order of magnitude of difference between minimal and maximal axial dimension of the finite element can be up to 7 order of magnitude, and Brick internal angle of hexahedral finite elements can be up to 180 degrees. The mesh is deliberately chosen to be as it is to prove the reliability, and reliability is proven. As we can see, the resulted curve is flat, and it is reliable for regular meshes or distorted meshes as shown. And we can see the thickness of the one of the layers in the present example is only 1/10 of the micron. So it is reliable. In this presentation I will show you only one example, but a very interesting example because it is extremely multiscale, and also we will trace the stresses in the optical fiber embedded between the layers of the composite plate, and we can see that material properties of composite are like that, so it is transversally isotropic, and also material properties of optical fiber are given here, and also of the adhesive that is bond between the composite layers, and that the dimension of the sample is 7.3 millimeters. It contains 26 layers. Layer thickness is 0.27 millimeters, and bond thickness is 0.01 millimeters. Optical core is very tiny. It is only 0.125 millimeters, and we will be interested in the stresses in the optical core, because if the tensile strength of the optical core is exceeded, we will also notice that the signal in the optical fiber is not good enough, not good anymore, and that is the purpose of this optical fiber in this undestructive testing. In this photo we can see the optical fiber between two layers of composite which are perpendicular to each other with fibers, and which is clearly seen here. In this slide we can see the specimen which will be used for the validation of the present approach, because the loading disturbs the specimen only very locally. The testing points can be very near, and the calculated displacement below the applied force is 1.1 millimeters for the applied force of 15 kilonewtons. And you can see the optical fibers, they are very tiny, and they are placed between first two layers of the composite. We can instantly notice that present finite element approach is a very good choice, because finite elements can differ in size up to 7 order of magnitude, and in that way we can have a reasonable number of finite elements in the model problem, not too much. So you will see in this slide we can see the results of the present finite element approach per 4 finite element meshes of the model problems which differs in size. The first model problem is of size 30 by 30, the second 40 by 40 millimeters, and then 50 by 50. This model problem corresponds to the experimental one, and the last one is 100 by 100. We will see that because of the special feature of the present example that applied loading disturbs material only very locally, there is no any difference how big is the finite element model problem far away of the loading. And we can see that for all 4 finite element meshes we obtain the maximal displacement, which corresponds to the experimental one. Execution time is 80 seconds. Number of degrees of freedom is 131,000, and number of finite elements is 8,000. Such a big number of degrees of freedom, it is because we have degrees of freedom also per stresses. In this slide, we will investigate topology of the present finite element mesh, the last one. And as you can see, the aspect ratio of finite elements goes from 1 to almost 8,000, which is 4 orders of magnitude. And also that brick internal angles goes from 8 to almost 180 degrees. And so let's recall that in finite element displacement based approach, we can have aspect ratio up to 4 orders of magnitude without disturbing the results, disturbing the accuracy of the results, and also only up to 40 degrees of internal angle. In present approach, aspect ratio in each of finite elements can be up to 9 orders of magnitude, which is almost on a nanoscale. And also the internal angle can go up to 180 degrees, so the brick can go transform to prisma, and we will be totally safe and accurate with results. Let us now start with visualization of the results. And firstly, we can see that maximal displacement is as measured one, and that there is no spuriosity in the visualization of the displacement field per component in the direction of the loading. Now let's see how it deforms. It deforms smoothly and nicely. It reacts on the mesh. Here we have a very skewed finite element. And now the other displacement and shear stresses, optical fiber. And also we can see the maximal stress component and how we see a bond between the layers, and also we saw the optical fiber, and also here optical fiber, and that will be everything about the visualization of the results. So per optical fiber, the maximal stress is 1 gigapascal, and we can see that optical fiber will feel that loading, and we will have the probably the loss of signal in the optical fiber. So the personnel will notice that something is happening with the protective composite barrier, and personnel can react accordingly. Let us now investigate the strain field in the direction of the loading. And as we can see, because this is in the perpendicular coordinate system, but If it is a natural coordinate system, we will have everywhere here the blue maximal values, so we can see that the strain is maximal on the edge of the loading circular area. In this slide, we will see how this model problem will be calculated in commercial software package, one of very good commercial software package, in which finite elements are seamlessly stabilized by mid-side nodes, seamlessly from the user. But anyway, we have bad convergence and also meaningless results for the final mesh. So as we all know, this is just confirmation that finite element displacement-based procedure cannot be used for the simulation, for such a kind of simulation of completely not approximated per geometry composite material. And we came on the last slide of this presentation. Let us recall what we said in this presentation. We noticed that commercial codes are based on the oversimplified finite element formulation and have huge library on the case-dependent finite elements. If finite element analyst is not well coached for at least 5 years by the expert, he will not be even aware of the deficiency of the finite element software he is using. Anyway, every finite element animation looks nice, but the accuracy is under question without validation. Even validation is expensive. Engineers will rather use more expensive experiments than finite element simulation, which is always less expensive. And maybe the answer for that, why engineers see the finite element technology as a commodity. It is because finite element software is like a cookbook. A good cookbook will not make a good chief. So it is not guaranteed that solution will be accurate. Even you give to the computer-aided design engineer the best software on the market, it is not guaranteed that he will provide you with the good results, with realistic results, with results which will occur in structure on site. Usually, the most common error in analysis of unskilled finite element analysts is that they put too much finite elements in finite element mesh, and that will increase the solution time, that will increase the error, that will multiply the error of the finite element results. And instead of using the same finite element formulation for so many decades, maybe now it is time to go further, and that software vendors invest in the new finite element approaches like the present one, in which finite element formulation is not sensitive to the errors of user in the making of the finite element mesh, in the quality of the finite element mesh. So in that case, we can have good computer-aided design engineers, good designers, which can simulate safely their designs and provide us with the realistic results. So thank you for attending my presentation. I hope you enjoyed. In the case of any questions, please be free to write me on my email, and I wish you a nice day. Goodbye.